Hello, welcome to Module 5 of Foundations of Machine Learning. Today we're going to talk about regression and move from linear regression to logistic regression. So I assume that by this module you've already watched and participated in Module 4 and are comfortable to some extent with linear regression in one dimension, that is to say with like a scalar input x, and you've at least seen n-dimensional linear regression. So when you don't just have one variable, but a vector of input variables. We did an example in Module 4. You're somewhat comfortable with squared losses for a simple example. So you've seen the loss, you've seen the empirical risk, which is the average loss. I assume that you have an understanding of the basic supervised learning pipeline, and you've seen trained test splits, at least at eye level. So when we obtain our parameters on the training data, and then we use those parameters to evaluate data in our test set. We have seen a good amount of NumPy, Pandas, and Matplotlib in the previous module, so I assume that you're comfortable with that. Now, I don't assume that you've seen logistic regressions before, because that's what we're going to be talking about today. By the end of today, you'll be able to explain why naive linear regression of the type we saw previously, that this is a poor model for binary classification. We're going to be able to define the logistic regression model. That's a linear score and then something called a sigmoid, and this is going to give us a probability. By the end of the module, you should be able to write down the logistic cross-entropy loss and connect it, or at least understand how it connects to empirical risk. I say that you should be able to derive, or at least follow, the gradient of the logistic loss for a simple example. We're going to get a little bit into calculus at this point, so you don't have to necessarily derive it yourself, but at least you ought to be able to follow what we're going to discuss today. You'll be able to implement and evaluate logistic regression in Python in a small data set. We'll give an example. You'll be able to compare logistic regression to a naive regression-based classifier and then a baseline. That's how we're going to end today. And then you'll be able to apply basic train test splits and leakage heuristics in a classification setting. So just to recap what we've seen previously in Module 4, we want to model a approximation to a real valued target t in real space. So there's a real valued number we want to estimate. It could be hours spent doing something. It could be somebody's steps per day, some real valued quantity. And we're going to try to estimate it with a linear function. That is to say, a function of x, but not x squared or x cubed and so on. This function is going to have basically a slope and an intercept, or a weight and a bias, or in other words, just a set of parameters, 0 and 1. I assume here now that x might not just be a single number, but it might be a vector of a few numbers. Therefore, we have the weight w sub 1 being itself a vector, and here it's just transposed so we can multiply these together. So all of this together is our function, and our parameters theta are w sub 1 and w sub 0, and all of this estimates an output y, which should be as close to t as possible, but might be a little bit off. When I say it should be as close to t as possible, well, we can actually measure that by the squared loss. So we have the residual, which is just the difference between our estimation y and the true target t. We square that difference, and then we divide by 2. And so that's a loss for a particular example. Over an entire data set with n examples, we can calculate the loss for the prediction for that data sample and the target for that data sample. And we can find the average of those things. So we just sum up all of the losses for all the data points, divide by n, that gives us our average, which is our empirical risk. This works fairly well when the noise in the data, like the difference between like what we observe in x and y and what is actually true, is confounded a little bit by noise. We always assume that there's noise in the world. We'll talk a little bit about Gaussian noise later, but we assume that the noise is roughly consistent. Again, the target is a real value. We assumed as much. And so far, we don't need probabilities, right? We're just estimating, but we don't care about necessarily the probability that target y is that value. We're just outputting that value of y. So our new goal is to go from regression, estimating something on a continuum, to doing classification, so estimating a nominal category. In this case, we're going to assume our category only has two possible values, 0 or 1, which basically is the same thing as true or false and true. So let's have an example. We're going to come back to this example several times. We have an engine. We're in an environment in which we're testing engines. We're in the aeronautics industry, and we have two possible outcomes for an evaluation of an engine, of a jet engine. The first is that the engine will fail within 24 hours. And then the other outcome is that it's going to be normal and it will not fail within 24 hours, so it can be kept in operation. So what we would like now is not just an estimate of it'll fail or it won't, but maybe we want an estimate of the probability that it's going to fail, right? So there's a big difference between there's a 99% chance that this engine will fail and there's a 50% chance that the engine will fail, right? Both of those outcomes might prompt you to investigate that engine, but there's still a big difference. So what we want really is probability, an estimate. So what is the probability that the engine will fail within 24 hours given whatever information we have about the engine in X? Okay. So this is a probability. I call it p hat. And because it's a probability, it's going to be in the range of 0 to 1. So at least 0, but also possibly 0, and at most 1. And then we can interpret that output as a probability, right? Or it may not necessarily be a true probability in the world sense, but in the sense of our experiments, we can treat it as such. So this model is basically going to be trained by minimizing an appropriate classification loss. We had a loss function previously. We saw on the previous slide, we're going to have to come up with a new loss for classification. And then, given that loss, that's going to tell us how well we're doing in making our estimates. We will still need a decision rule that, given the probability, given a model trained with the classification loss, we'll be able to make decisions that will match our costs in the real world. So imagine we're in an airline, we're monitoring jet engines for our fleet. And for each engine, we're going to log telemetry from the first few minutes of a flight. So we'll look at the vibration in RMS. Don't worry too much about the aeronautics of all this. We have two variables. We have vibration in RMS in G, and we have the oil temperature. How many degrees in Celsius above nominal is the oil temperature? So obviously, if you were actually working in an airline, you'd have many more features than this, but just for the sake of the example, let's imagine we have these two variables of input. So these two variables together is a little vector x. We're going to have a target. The target, again, is a binary outcome, y. Y is an element of the set 0 or 1. Either it's false or it's true. True means there's a failure within 24 hours. 0 is normal operation. So the first thing we'd like to think about is our decision. Our decision is that we want to flag engines that are likely to fail soon so that we can intervene with maintenance, or at least investigation. And what we would like is predictions to be a probability, like I mentioned a few moments ago. Part of the reason why we want to have this probability is so we can better interpret our outcomes, and the kind of outcomes we can have now are connected to the kinds of errors we can make. Those kinds of errors include false negatives, in which case the model says, this is a negative case. I do not expect the engine to fail, but that's false. It actually does. There's a huge cost associated with that. If we let an engine or a plane fly with a faulty engine because we missed maintenance, that's a very large risk. I think you can agree. But there's also risks in the other type of error. So the other type of error is the model says that this engine will fail, but that isn't true. It's a false positive. So what we would do in that case, we would trigger some decision rule to go and investigate and perform maintenance on the engine. We didn't need to, so it's a little bit of extra cost that we have to, deploy our team, pay them, maybe use some resources. But generally, that cost might be less than having an airplane flying around with a faulty engine. So we talked about linear regression before. So we can try to use linear regression, basically fitting a straight line to our data. We know that x will be whatever variables we have in our independent variables, and then y is our dependent variable that we're trying to predict. We can imagine that this binary case is a continuous target, so it goes from 0.0 to 1.0. It's going to be the case that all of our values all of our targets are going to be either 1 or 0, as opposed to being nicely spread over the range like we saw in linear regression. But we can just imagine that this is a standard linear regression task. So once again, we can fit our linear function here we talked about a moment ago, make predictions about the outcomes, and then we'll just keep on minimizing square loss like we saw a moment ago, right? Look at the difference between our predictions and the targets, square it, average it, and we should be good to go. Because we're fitting a line through this space, this line will give you estimates on the y-axis, and then generally that line will pass through 0 or 1, so we can maybe interpret the fit of this line. We can interpret it as a probability. We'll see if that's true or not. We can set a threshold to the space. We can say, if the linear regression predicts an outcome, like a prediction of y prime that is less than 0.5, assume the engine won't fail. If it's above or equal to 0.5, assume the engine will fail. So already we're getting some problems. So the first problem is that in a linear regression, there's no guarantee that the y prime will actually lie within 0 or 1. Like a line that goes through this space, you can imagine will keep on heading downwards infinitely and upwards infinitely, and we can't describe probabilities by anything less than 0 or greater than 1, so that doesn't really make sense right off the bat. The squared loss we saw before is a measure of distance between estimates in data space, but this doesn't really reflect probability or probabilistic correctness. So we're kind of maybe optimizing for the wrong thing in the first case in terms of our residuals. And also it doesn't really help us correct for overconfident predictions. So predictions that are very wrong should be penalized more than predictions that are just slightly wrong. So here's a synthetic data set again, and with these blue dots. So these blue dots are observations from previous engines. And as I mentioned a moment ago, all of the outcomes are either it's a failure, is imminent, or it's not, is a binary. So all the dots are spread out across y equals 1 or y equals 0. We have the true probability, which I estimate through this orange curve over here, and then I have the naive linear fit, which we obtained from doing the least squared linear regression we saw in the previous module. So as you can see, as I mentioned before, right now this line down here is extending below 0. So does it really make sense that when x is -4 or less, the probabilities of less than 0 are possible? No, certainly not. And also the line will keep on extending upwards beyond y equals 1. The actual relationship in the probability between x and y, shown here by this orange curve, is clearly nonlinear, but I'm kind of forcing the model to assume that it is by fitting a linear a line through the space. And what I would rather have is a model that respects that I'm on a range of 0 to 1, and that I have some probabilistic structure behind the scenes. It's not just a linear phenomenon. So the solution to that is using a different curve that follows a shape that's much more similar to what we saw a moment ago. So this S-shaped curve is called the sigmoid function. Sigmoid is the Greek character for S. I'm going to show you what that actually looks like in a second. So it's sigma is the Greek character for S, and the sigmoid is called such because it kind of looks like an S. To a couple of important things here. First of all, this function, as you extend it further and further to, in this case, z, getting more and more negative, the curve will never dip below 0. So 0 is the absolute minimum, and it'll never rise above 1. So already we have a function that respects the rules of probability by never estimating anything more probable than 100% or less probable than impossible. That's the first thing. So we kind of respected the bounds of probability. The second aspect here is that there's a shift here which is happening, which is nonlinear. So generally the function is very flat initially, where we estimate that the probability of an engine failure is very low for a range of input values. Then it suddenly rises at a certain point, by which we'd make a decision that at this point, there's going to be a probability of error. And the function, I'll show you in mathematics mode soon. It looks like this. So you can download this code. This sigma function is literally this blue curve you see over here. is this 1 over 1 plus the exponent of minus z. I'll show you this in math form in a moment, but this function over a range of z gives you this beautiful, nice-looking curve, which shows up very often in machine learning. So the general idea behind logistic regression is that logistic regression fixes the various problems of linear regression by modeling the probability of a class, specifically the class 1, directly. We're going to do this in a few steps. The first step is I'm just going to gather in my parameters like I did previously, again linearly. So I have a vector of variables x, and I will still transform them with my parameters w sub 1 and w sub 0. So I'm still kind of doing linear regression so far, but linear regression will now go into a variable z. This variable z, or a representation of my linear estimate, will then essentially be squashed into the sigmoid, which we see here. Now, this is the good mathematical rendition of sigmoid, sigma, which we saw in the previous slide in code. It's 1 over 1 plus e to the minus z. And here's the Greek character sigma, from which the sigmoid function gets its name. Okay, so this function gives us that nice S-shaped curve, and z is the result of a linear transformation that we've learned its parameters. Now, because sigma of this linear approximation goes between 0 and 1, we can say, well, given x input, the probability that the outcome is 1, in this case that the engine will fail, is given directly from sigma. So that's our probability. So we get our probability estimate directly from sigma. So first of all, we guarantee that probability is on this range. Actually, I should have made these square brackets. I should fix this before I post it. But it could be, because this probability could be absolutely 0 if z is infinitely small, and it could be 1 if z is infinitely large. But that be as it may. And this fits naturally within the idea of a Bernoulli likelihood for the Bernoulli distribution. So now we have a function that replaces our line model, our linear regression, to give us basically a probabilistic output, which is great. We're making some progress. If our model is now estimating probabilities, and it's not just estimating outcomes or like targets, we're going to need to change the loss function. So the loss function we have now is something called the logistic loss, shown here. So we still have our script L. Script L still refers to the loss. How bad is our estimate? Log stands for logistic. And logistic, as the name suggests, is composed of these log functions. We talked about this a little bit in module 4, but just to go over it again, this function is essentially a function of two terms. One term is y times log of p, and the other one is 1 minus y times log of 1 minus p. What this is saying is, well, y, remember, can be either true or false. Either there's an engine failure or there isn't, and this is what I'm trying to predict. If a data point actually is an engine failure, y will be 1. Therefore, this y will be 1, and then I have log p is what is left over in this first term. If there is an engine failure, then this term will disappear. 1 minus y goes to 0, and I ignore this entire term. 0 minus times log is 0. And all I'm left with is minus log of p. And this is great because now, as you can see from this, we have, if the value of p is very like close to 1, then this will be relatively small, right? So minus log 1 will be fairly close to 0. But if my estimate for this true outcome, like this engine actually did fail, but my estimate for its probability of failure is close to 0, then my loss, the how wrong I am, will be very large, right? 1 minus log of 0 will be close to infinity. Will be very large indeed. The smaller and smaller the probability is, the further and further away we are from the truth. And I'll leave it as an exercise for you to see why this chain of reasoning is also true for the inverse case, where the true value is 0, when the engine didn't fail. I'm still going to estimate probabilities of failure in this case, and you can see that the value of, I can evaluate how good my probability estimate against that outcome. And just to maybe make it a bit more helpful here, I've graphed the predicted probability of the engine failure in both cases where the truth was that there was an engine failure, which is the blue curve, and the case in which there was not an engine failure, the orange curve. So that is our loss. I hope this makes sense. This is one of our learning outcomes today, so hopefully this makes sense to you. If it not, pay attention to this slide. Then remember the empirical risk, or the objective function, as we called it previously, for the entire data set, is the average loss over all of our data points. So we just, again, take the average by summing over all of our n data points. We compute the loss for the prediction probability versus the truth, and then we divide by n to get the average. So the training logistic regression is trying to minimize this average loss, right? And we want to be as close to the supposed truth as possible. So if we're only dealing with binary accuracy, so eventually we're going to have a decision, and then we can have a model that we've trained to say, yes, I predict failure, or no, I don't predict failure. This will often hide important differences in the model. Right? This is why it's important to be able to open up the opaque black box, so to speak, and understand what the model is actually doing under the hood. So once again, I'm going to zoom out for your own benefit. One day I'm going to adjust the driver for my camera, but today is not that day. So here's a little bit of code. We have a array of true values. So the first two jet engines did not fail. The next two jet engines did fail. So this is the true value I'm trying to predict. I have three models I've learned, each of which is outputting probabilities of failure. And you can see those here. So the first model, for example, says there's a 49% chance of failure for the first engine, a 49% chance of failure for the next, a 51% chance of failure, and so on. Now, what I have here is a little decision rule. If the probability of failure is greater than or equal to 50%, if there's a 50% chance or higher of failure, predict failure, otherwise predict no failure of the engine. And I'm going to use that as my decision rule. That's going to be my y hat, my estimate for failure. And then I'm just going to take the average. This is our loss. And we'll take the logs here to get the log loss, because that's what we're dealing with given the function we saw a moment ago. Now, you can go through this yourself, and you can actually run this yourself to satisfy yourself that these results are accurate. But each of these models, A, B, and C, are going to have the exact same accuracy according to this decision rule, and they're all going to be perfectly accurate. Okay, but the first model has a log loss of almost 0.7, and then model C has a log loss of just 0.01, right, which is orders of magnitude lower, depending on what your magnitude is or what your order is. It's a lot lower, right? So Model C is clearly much more attuned to the truth than Model A is, but if we're only looking at accuracy, these models will look indistinguishable from one another, which is a big problem, right? We need to understand what's... All right, let's take a brief moment here and take a deep breath, because we're going to dig into the calculus that I warned you about earlier. It's going to be light, and I'll try to take it slowly. So remember, we have a model that is now based on the sigmoid function. So this is the sigmoid function over here, sigma of z, which gives us our nice nonlinear S-shaped curve. And we can represent this in a few ways. So here's our familiar function sub theta of x. This is just the linear combination of our parameters with x passed through the sigma function. So we have our loss, which we saw a few slides ago. This is unchanged. So this basically tells us how far away our predictions are from the truth, and then in probability space. I'm doing something slightly different here. So I've changed script L sub log to L of theta, and then semicolon x and y. So the semicolon is not entirely a standard format, but it comes up an awful lot in machine learning. This is it serves almost the purpose of a conditional in the sense that I'm interested in this being a function of theta. So I'm trying to model this as if theta is the thing I'm changing, the variable, because I am going to change it because I'm going to do learning now. I want to say I'm given x and y, because in some sense we are given x and y. These are our data points, and they're not going to change. But I don't put that straight line, that vertical bar between theta and x and y, because this isn't a probability in which it changes conditionally. The probability of theta changes conditionally on x and y. That isn't really the case. Sometimes you're going to see functions like this where you could use a semicolon to say, well, I am provided with x and y, but really this is a function of, in this case, theta. Sometimes you see this written as script L sub xy and then just of theta. But regardless, this is just our same old loss function, but now I'm looking at it from the perspective of it's a function of theta. Okay? You'll remember from a previous module, we wanted to work in theta space or in parameter space because we wanted to change our parameters in such a way that our loss was minimized. We talked about quadratic convex surfaces where we minimize that loss by going down that curve to try to find the lowest possible average loss, which is the whole point of machine learning. Okay? That's what we're going to do again now. Okay? So our key result, given our loss function and given the shape of our actual model, will be that the gradient with respect to the parameters of our loss function will be equal to just our output of the model from sigma minus y, right? That's our target, which in this case is binary, so it's either positive or negative. All of this times x, which is our input variables. Okay, so this is the key result. I'd put a box around this if I were you. I'd even write this down in your notebook if you have that open. Like I'm not likely to keep on testing you about what this equation looks like, but it's going to be important. So just try to just write it down. It'll help with the learning process. I'm going to walk through the steps indicating why this is the way it is. Okay, so Z is the output of a linear regression of just theta times x. So this is our good old-fashioned linear regression. We have parameters theta. These are the things we can modify in our function. And I'll just call this whole linear regression Z. The probabilities that I'm estimating, call that P, is the output of sigma of Z. Okay, we saw this earlier also. I'm just passing my linear regression into the sigmoid so that I get something that looks like a probability. I'll call that thing that looks like a probability P. And I have my loss function once again. Now, we want to differentiate the loss function and eventually get down to with respect to theta. So this upside down triangle, sub theta, means the gradient with respect to theta, right? The partial derivative of my function, which is my loss function, with respect to theta. Again, we saw this earlier. We have a massive surface in space. The parameters we can change are theta. Those are the parameters of the model. And that surface basically tells you how well you're doing in making predictions. That's the empirical risk. That's the average loss. And I want to set my parameters in such a way that I get down to the lowest point in this surface as possible. And just like before with module 2, we want to, or was it module 3? In the previous module, we want to find from where we are what is the direction on the surface that changes most rapidly downwards, and then head in that direction. Right? We want to head selfishly, quickly, straight down as quickly as possible. Okay, that's why we're doing this differential. So we're going to do this in parts. Okay, so first I'm going to differentiate the loss function with regards to P, which I previously called sigma of our input. Okay, which is this whole big thing here. So the differential of the loss with regards to P, we can break down, here's our loss function over here. We can perform this differential in two steps. We have this term and that term, both of which this negative will apply to. So we have minus y log p minus 1 minus y times log 1 minus p. So take this first term, which is minus y log p. Y is essentially a constant, so we kind of leave it alone. Log p is our function of p, which is the variable against which we're trying to differentiate. We know, and you may remember, that the differential of log of p with regards to p is just 1 over p. P could be x. The differential of log of x with respect to x is 1 over x. So that's why this term over here becomes this term down here. Here's the minus is carried down. The y, being treated as a constant, in this case, because I'm differentiating with regards to p, is brought down. And then the differential of log p with regards to p is 1 over p. That's why the p comes down here. And I'm halfway there. So I've differentiated half of my loss so far. Next, we differentiate this longer term, the second term, again with regards to p. 1 minus y is not a function of p, so we can treat that as a constant, and we just bring that down over here. And the derivative of log of 1 minus p will be 1 over 1 minus p, which is this derivative, times the derivative of minus p, which is minus 1. And then this minus multiplied by that minus gives us our plus, which is why we have this plus here. So we finished doing the differential. The last thing we have left to do is maybe just to combine these terms together for simplicity. And the way to do that is to look at our denominators and make sure that the denominators for our two terms are the same. To do that, we can multiply the first term by 1 over p, by 1 minus p divided by 1 minus p. That will give us a denominator of p times 1 minus p. And we can multiply the second term by p over p. This will give us a denominator of p times 1 over p. And then that's why both of these denominators have become p times 1 minus p, which is down here. 1 minus p times y, or minus 1 minus p times y, plus p times 1 minus y. You can work this out yourself as an exercise, becomes p minus y, and I'm done. I've differentiated my loss function with regards to p, which is my sigmoid function. So far so good. I'm not quite there yet, however, because remember p is itself a function of z, and z is our initial linear function, which has those parameters that we're so hungrily after. Okay, so we still have more differentiation to do. Well, what is the differential of p with regards to z? Because we've previously done differential L with regards to p, but p is sigma of z, so we have to keep on going. I'm going to leave this for now. I might post a link later to maybe walk through the steps, but through a logic that uses a lot of the same steps that we saw a moment ago, the differential of sigma of z with regards to z will eventually translate into this neat little function, p times 1 minus p. Okay? So the differential of this with regards to z is just sigma z times 1 minus sigma z. So far we have differentials that are nice and crisp and clean and minimal, which is nice. Now, again, I want this loss function to be in terms of theta at some point, so I'm going to have to combine these functions together. If I wanted to get the differential of my loss function with regards to z now, which is, again, my theta times x, I can use the chain rule. So the chain rule basically just says, well, that the differential of L with regards to z is the same as the differential of L with regards to p times the differential of p with regards to z. And then I welcome you to do this yourself, but p times 1 minus p, which is the differential of p with regards to z, times this fraction, which is the differential of L with regards to p. The p times 1 minus p will cancel out, And all I'm left with is p minus y. So this is even more minimalist than previously. So I have my estimate, and I have my true target, which is very similar to the residuals we're dealing with in the first case. I'm not quite finished though, right? Because at the end of all of this, I really want to do a differential with regards to sigma so that I can be in that space where I have my empirical risk surface, and then the variables that I can modify to move down the surface are just in terms of theta, because I want to change theta to get down to the minimum point in that surface. So the differential of z now with regards to theta is just going to be x, okay? Because remember, z is just a linear function of coefficients in theta and x, and the differential of all of this with regards to x, you know, anything without an x will disappear, and I'm left only with x at the end. So anyway, the gradient of my loss function with regards to my parameters, which is what I care about in the first place, is again applying the chain rule. So applying the differential of L with regards to z times the differential of z with regards to theta will give me the differential of theta of L with regards to theta, which is just p times y times x, and this is the quantity that I was after in the first case. So all of that, you know, a bit under the microscope, but this is a very simple function that I was after all along, and this will allow me to do machine learning in our logistic case, where I have that nice nonlinear sigma function that can estimate things that look like probabilities. I can now do gradient descent by just tweaking my parameters theta to make the loss on average go down and down and down until it gets as low as possible. So here's just a little kind of a little numeric gradient check. Again, this is under the microscope. Download this code and try it out yourself. What's going on here is I have my logistic loss function. So again, here is my sigma. Here I'm calling it P instead of S because, you know, P is the probability I'm trying to estimate. And I'm just going to return the loss. So I have my parameters theta. I have my linear estimate, which is just theta times x, where x is my input. And I have my true output y, which I'm trying to estimate. You can see kind of clearly here that this is the in-code version of the loss function we saw in math form before, right? Y times log of p plus 1 minus y times log of 1 minus p, all negative. And then we have this function defines our logistic gradient for a single data point. So again, we have an input x. This is passed through a linear function giving us z. That linear quantity is passed into our sigmoid, which gives us p. And then we just return p minus y times x, which is the gradient of the loss with regards to theta that we computed a moment ago. Now what's happening in the rest of this code is that we're generating some data, we're generating some random parameters, we're generating some random values x, and we're providing like y is true. Like, so back to our example, this is a case where the proverbial jet engine fails. So epsilon here is 1 minus 1 times e to the minus 5. I called this eta previously. This is just the learning rate. I have a basis function. I went over this very briefly in the previous module. This just allows us to do like vector arithmetic quickly, so we can multiply theta by x. And then the only thing that's happening here is that I want to compare the difference between the outputs of my logistic gradient. So this is the implementation of our gradient function. So like the function that tells us how to move theta in order to minimize the loss. How does that compare with just basically doing little tweaks to theta? So here I'm taking my parameters and adding a little bit of noise, which is here epsilon, and subtracting a little bit of noise. So I'm just jiggling my parameters a little bit. I'm making the parameters a bit bigger, making them a bit smaller, computing the loss, the direct loss, given those slightly different mutated versions of my parameters. And I'm looking at what is the average, what is the average of these two things, right? This kind of basically tells me like the difference between a little bit above and a little bit below, which is kind of an estimate for a difference, which fundamentally is what we're doing in terms of differentiation. I mentioned earlier that I usually called EPS eta, and that was not correct. EPS here is epsilon. It's a little bit of noise that I add or subtract to a function. This is in contrast with the learning rate we saw previously. And then the final thing I'll do here is I'll output the gradient from that I've obtained theoretically in the previous slide with whatever the difference is by choosing a parameterization or model that jiggled a little bit in the positive direction and jiggled a little bit in the negative direction. And what is the difference between these two things? Those two quantities should be extremely close to each other, as long as epsilon is small, because I'm looking at differences in these points. And fortunately for us, especially given all these random number generators, the analytic gradient, so the one we've obtained from our theoretical process from the previous slide, and the one we obtained from just merely jiggling the parameters a little bit to see in which direction the loss will change the most. These are exactly the same in this case. So why did we do all of this? So this is looking under the hood, right? We're scientists and engineers. We're not just users. We wanted to, again, understand that we're trying to minimize empirical loss or empirical risk by moving our parameters theta in our model. And now the parameters parameterize the sigmoid model. So we wanted to basically do the same thing we did with linear regression. We needed a different loss function, so therefore we needed to compute a different derivative function to move down that curve. So we did that theoretically previously. Now, it can be easy to make mistakes, and sometimes these functions are not so easy to find closed forms for. So we did this little numeric experiment by jiggling our parameters a little bit around the current parameter set, looking at the differences between what the loss is, and then using those differences to estimate what the differentiation would be, or what the gradient would be. So this is something we actually do in practice. Sometimes we have the fully derived math in a closed form for the gradient. Sometimes we might not. Either way, sometimes you want to be able to confirm that your theoretical gradient and your empirical gradient or numeric gradient are as close as possible or identical. This is especially true when you're trying to implement your own custom losses. It's like like here I'm giving you the loss function we're using, but maybe you came up with a brilliant new invention, a brilliant new loss function that you want to test out. Maybe you're using your own optimizer. So like right now we're just doing simple gradient descent and just going down that empirical risk surface to try to find its minimum, but maybe you have a different approach in which the gradient is potentially used differently. And also just doing some basic debugging. So it's good to have kind of two views on the same process. This is a kind of tiny scientific experiment, right? So we're keeping everything else fixed. We're perturbing one little parameter slightly, which is theta in this case. We measure how things change. We compare what we observe through, doing this little perturbation, this little experiment. We compare it against our theory, in this case, our mathematical theory, and we see if things line up, and they do, right? This is like science at its core, right? We have a theory that we have obtained from a theoretical process, mathematical process, and our numerical experiments can confirm or deny that it's correct, and so far everything's lining up. So far so good. And like we saw a moment ago, like these numeric gradients and the theoretical gradients should be close if the theoretical gradients are to be trusted. So let's pop out of the microscope for a little bit and get back to our overall story. So logistic regression gives us essentially probabilities that an outcome is true given some input x. But we're going to have to make a decision at some point, right? We have a range of probabilities. We're going to have a threshold, at least in this part of the story. We'll need a particular threshold that says, we'll call it this threshold tau, and that will tell us if the probability is above or equal to tau, our threshold here, then predict 1, otherwise predict 0. So we're doing binary classification. So let's start with tau equals 0.5. So if the positive outcomes, like or the false negatives and the false positives, are equally bad, and I don't really care if I have a false positive or false negative, then maybe setting tau equal to 0.5 is fine. In our scenario, in our early warning scenario that's predicting if a jet engine is going to fail, missing an actual failure might be worse than merely sending a team to do an inspection that isn't necessary. Okay, so we might lower that threshold a little bit. If you lower the threshold tau, then you're going to end up, having lots of outcomes that have probabilities above, in this case, 0.3. And we're going to say those are going to be thought of as positive outcomes. Even if something is 31% likely or probable, I'm going to assume that this is true, it's a failure. And you can see how this will potentially result in a lot of false positives, right? So if something's only 31% probable of happening, like you and I know it's probably, like it's a low probability. But you better be safe than sorry, better send somebody out to inspect that jet engine, okay? And because we care more about the cost of a false positive than we do about a false negative. So here's like an actual walkthrough of this example. Let's see the head of the data. So here I'm going to randomly generate 3,000 flights using the random seed 3151. And like we mentioned earlier, we'll have only a couple of measurements. We'll have the vibration in RMS here, and we'll have the oil temperature data above nominal. Just for the sake of the task, I'm doing some clipping here to make it a little bit more realistic, although this whole scenario is very simple, but you get the idea. We're going to have a risk score, right? So a risk score that we compute is sort of given to us. It's 1.3 times vibration plus 0.18 times oil temperature delta is our risk score. And the true value of Z is going to be 10 times the risk score minus 3.2, so it's a nice linear function still. So this is basically like our true model of the world that is generating data, right? It's generating vibrations and oil temperatures, this is a function that describes risk, and I can pass this risk through this sigmoid function. So here's another sigmoid function, and then from the probability I can estimate this binomial distribution that predicts failure within 24 hours. This is our actual data. So I mean, what I'm doing down here is all behind the scenes. I'm generating synthetic data. So that's why I have a secret omniscient view into the nature of the world that allows me to generate these outputs. These are the true values of failure within 24 hours. In principle, you and I would only get the spreadsheet that would have been generated from actual measurements, and these measurements also might be a little bit imperfect depending on imperfections in the sensors. And then failure would have been the outcome of whatever process the airline has before they give us the data. Okay. Anyway, this is the scatter plot of all of our data. We have these two variables. These are the input variables we've been calling X, the vibration and the oil temperature. And this is a bit of a complicated one. So down here we have non-failures for low vibration and low oil temperature deltas, no failures for relatively high vibration and high temperatures above nominal. And then down here in yellow, these are all data points in which we've measured vibration and oil temperature, and we have jet engine failure, okay, indicated by its color. So once again, we're going to use sklearn to just split all of this data we've obtained into training sets and test sets. So we have train and test for X and Y in each case. In this case, I said we're going to take a quarter of the data, hold it out for testing. So far, so good. I'm going to fit a linear regression to this. So I'm going to go back in time a little bit. Imagine we haven't learned everything about logistic regression. And imagine I'm still just fitting straight lines to my data. So that's what's going on here. I fit a linear regression, or here I create the linear regression and then I fit it. And then I'm going to make predictions on my training and test set. Normally, like making predictions on the training data is what the fit process is doing, but I'm going to want to, measure it now just for my own sanity check, so to speak. And, moving on a little bit, down here at the bottom, I have my decision score. Right now I'm going to the scenario in which, a false positive and a false negative are equally costly. So I have a threshold tau of 0.5. Probabilities above this threshold are imminent failures, and everything else is not. It's all systems normal. And eventually I want to, compare those outputs against the truth, and I get, on average, an accuracy of 63%. So this is how well a naive linear regression-based classifier that we've been dealing with in previous modules would react to this kind of scenario. So now I want to compare that against logistic regression. So we're not going to actually implement everything ourselves. We're just going to go back to sklearn. We're going to import the logistic regression architecture. We'll create it. We'll once again create it with a random seed of 3151. We'll fit it to our training data and our training inputs and our training outputs. We'll predict probabilities. We'll compute our accuracy scores, and then we'll compare that against a baseline that always predicts the training positive rate. That's basically a majority class classifier, or it's similar to it. Just count the number of times that the positive class occurs in our training data, and estimate that is the probability of failure. So this super simple baseline is not a function of X at all. It doesn't factor in the oil temperature or the vibration whatsoever. It just says, well, the positive class occurs X times in my training data. It occurs 70% of the time in my training data. So I'm just going to estimate for every input that there's a 70% chance of failure. You can see how that's extremely simple, but it's not completely devoid of reasoning. 70% of the time in all of the data we've collected, there is a failure. So this is not completely brainless, although it's close to it. So here is the outcome, which you'll see yourself when you run this code. This is our super simple baseline that merely predicts the probability of a failure given the raw probabilities of the labels in our training data. On testing data, it gets an accuracy of about 58%. And this is the lowest of the three models we'll compare. The naive linear regression, which we just talked about a moment ago, I'm just going to fit a straight line through all of these data points. We're not going to compute the training log loss because there is no log loss for linear regression. Remember, we're just doing the mean squared error in linear regression case, so there's no log loss to speak of. But we're still passing its information through our threshold of tau equals 0.5. And after we fit a model linearly, given our values of inputs, we now have a 63% accuracy on our test set. Logistic regression, which we've set up according to our method we mentioned earlier, and according to, internal to that one line fit, it's doing gradient descent according to the function we derived earlier. We can compute the training log loss because we're actually doing log loss now, and we can finally compute the test accuracy of this system on the test data, and it wins, not up by as much as one might like. You might get slightly different results if you change the random state here, because there's a lot of random number generation going on. If you generate slightly different data, the numbers are going to change somewhat. Maybe occasionally naive linear regression will even beat logistic regression. That is possible. If you do enough experiments, you're going to eventually run into results that are unexpected or rare. But we're done. So we've made a slight improvement here, and not only have we made an improvement empirically, but we've kind of done the right thing by recognizing that we're dealing with probabilities here, and now logistic regression can give us a better estimate of probabilities than naive linear regression can, like we talked about earlier. Okay, so we've managed to make improvements on both empirical fronts and on theoretical fronts. So just for completeness' sake, here's the decision boundary. The code isn't really that important right now to the story, but what's drawn here in this dashed red line is the decision boundary between positive case and negative case. And this is a really tricky data set, actually, right? Because there's no single line you can draw through this data. There's no like linear regression we can perform in which all of the purple dots or the negative cases will be on one side of the line, and all of the positive cases or yellow dots will be on the other. Like there's no line in which these two are the endpoints of that line. Okay, so this is a more challenging data set than the ones we saw earlier, where like all of the negative points were on one end of the scale and all the positive points were on the other end of the scale. So this is a little bit more realistic in that sense also. Close here in the middle is where we ought to be undecided. Like this is where the models say, I'm really not sure if this should be a positive or negative case. You can see that all of these cases here are positive classes. So this is like again a problem of the complexity of the data. Eventually, we're going to see models that can handle this case very nicely, but we're building up to that bit by bit, step by step. We saw a couple of 3D diagrams earlier. So this is just the probability surface, the probability of failure, being true. Which is the up-down axis, and this is a function of our inputs, vibration and oil temperature. So you can again play around with this a little bit, and you can see how things change, like how likely something is given our inputs. This won't be that informative to us because again, like the decision boundary we saw a moment ago is made complex by the fact that the data is not linearly separable. But I really invite you to look at this code, download it, run it, play around with it, and try to interpret it. So we've talked a little bit about these kind of matrices before. So these matrices compare predicted labels versus true labels. These are called confusion matrices. Once again, the code is available to you. And generally, things are better than chance. Again, we're setting the threshold at 0.5, and where the model predicts like inactive, so in other words, like lack of failure, the true label is 352, and this is a relatively large number. So like you can see here, the color represents amount of overlap. So there's often a lot of agreement between the prediction and the true labels. Unfortunately, there's also a lot of agreement or disagreement between inactive predictions and active true labels. Okay, so now we have a lot of counts of cases where the predictions don't necessarily match the truth. So we have a lot of counts for data points that are off of the diagonal now, and this is kind of reflected by our lower accuracy score. This is a different experiment than earlier, so we have slightly different results. But you can play around with this. So I want you to download this code, integrate it into the overall learning we saw earlier, and now start actually turning the knobs. So we've been dealing with tau, the threshold of making decisions, at 0.5, make it 0.3 like we recommended, maybe make it 0.7, and see how things change. Okay, so see how the confusion matrix will change, and we'll leave it at that. You have to be careful at this point, actually, because I'll just flag this for you. We previously mentioned that you don't want to adjust anything in your experiments where the results on your test set will make you go back to the training data, adjust something, get a new model, and therefore new results on your test set, and then keep on doing that until your test set error is as low as possible. So if this is the test data, and I go back and try a different threshold and get different results which are better than the ones I previously defined, and then say, oh, this is my good setting for tau or my threshold, then that's the kind of cheating we mentioned earlier with the information leakage. Okay, we'll talk a little bit more about how to avoid this soon enough, but basically, if we have a hyperparameter, a parameter outside of the model, like the decision boundary tau, then we have to adjust that before we actually get to the test data. I'll mention that over and over again in this class, just because of how important that aspect is. Okay, but still, we're not doing deployment now. Now we're just getting our hands dirty and learning how these things work. So feel free to adjust anything your heart desires. So going back to the use case, which metrics matter? So this is an early warning system. False negatives mean we'll miss an engine that could fail because we'll have no inspection, and therefore a tragic accident could occur. If is a false positive, so the model says this is positive, which means that the engine will fail, but we're wrong. We've sent a team to inspect it unnecessarily. The engine's fine. That'll cost us something, but certainly it'll cost us less than the false negative. So this is a pretty clear case of the difference between the costs of these two types of error, but we'll always have to do some kind of trade-off. The degree of that trade-off, and indeed even the nature of the trade-off, will depend on the nature of the task, the data, and even the stakeholders. So it's really a case-by-case issue. So logistic regression, this new model, this is basically the second of our learned models we have presented so far, and various generalizations, which we haven't talked about yet, underpins an awful lot of real systems in the real world. So like ad-click prediction, so whether or not you're going to click on an ad that's shown to you in your news feed or your search results is often logistic regression under the hood because it's quick and dirty and usually pretty good. Email spam filters are often based on logistic regression. Risk scoring, so whether or not you're going to default on your credit, whether somebody's going to fail or not in a class, whether someone's at risk or not of having a medical issue or diagnosis. Logistic regression often is a very good baseline that is often very hard to beat, especially if the data sort of are appropriate for that kind of learning. Also, even in many neural networks, we're also going to have a sigmoid function or something that looks like a sigmoid function, and we're going to have cross entropy, the cross entropy function we saw earlier, to basically serve in the output layer. So even though we're dealing very simply with regression fed into the sigmoid functions that lead us to a particular kind of loss function, this building block of machine learning will make its way into even some of the deepest transformer-based neural networks we're going to see later in this course. So some open questions to think about. Maybe write this down in your journal. How do we keep the probabilities calibrated when we have models that have far more parameters than the ones we have been dealing with so far? How can you make logistic type models robust to distribution shift and other kinds of feedback loops? By that I mean, if we've fit a logistic regression to a particular set of data, and then we deploy the model in real life, but then the nature of the data changes so that the probabilities that we've sort of estimated no longer really reflect the true probabilities of the data generating process. How can we adjust things? So again, open-ended question. Think generally about it. Here are your quick checks. So again, this is all on the website. So I want you to. There's a bit of an error here. I'm going to correct that mathematically, but again, for your own benefit, go online, answer these questions, bring them to class, and I'm going to look forward to seeing you in the next module, Module 6.